In this video, we're going to discuss the solutions to the final exam on multivariable calculus from summer semester 2018. The exam contains 9 problems on the following topics. In the first problem, we're given a vector function. In general, we can write down this vector function as a 3-tuple vector. So the first component is going to be cosine of tt, second component is sine of tt, and the third component is simply 3t. On the A part of this problem, we need to find the derivative of this vector function, which is going to be again a 3-tuple vector. The derivative of this part is going to be minus sine of tt multiplied to the t according to the chain rule. The derivative of the second component is going to be cosine of tt multiplied to the t, and the derivative of the third component is simply 3. So on the second part of this problem, we need to get the equation of the tangent line. Then the equation of the tangent line at this point t0, which is pi over 4, is going to be equal to r of t0 plus r prime of t0 multiplied to the t. So in order to get this equation in a vector form, first of all, we need to substitute this t0 to the r into the r prime and get a t vectors. So the r at the t0, basically at a pi over 4, it's going to be cosine of pi over 4 multiplied to the t multiplied to the pi over 4, sine of t multiplied to the pi over 4, and simply 3 multiplied to the pi over 4. So the cosine of pi over t is going to be simply 0, sine of pi over t is 1, and the last component is going to be 3 pi over 4. Now let's calculate r prime at this point, t0. It's going to be minus t multiplied to the sine of pi over 4 multiplied to the t, cosine of t multiplied to the pi over 4 multiplied to the t, and simply 3. So the sine of pi over t is going to be 1 multiplied to the minus t, it's going to be minus t. So t multiplied to the cosine of pi over t, it's going to be simply 0, and this is 3. So the equation of the tangent plane would be the vector 0, 1, 3 pi over 4 plus another vector minus t, 0, and 3 multiplied to the t. So if it multiplied this vector to this t, it would be each component of this vector multiplied to the t, minus tt, 0, and 3t. Now we can add these t vectors component-wise. It's going to be minus tt, 1, and 3t plus 3 pi over 4. So please note that whenever you put some tt here, it's going to give you a point on the tangent line, and the point is going to have the 3 components. This first, second, and the third one. The first component means the x component, the second one means the y component, and the third one means the z component. So actually we can write down this vector function as a parametric equation in the form. So x of t, it's going to be minus tt, y of t is going to be 1, and z of t, it's going to be 3t plus 3 pi over 4. So this is the parametric equation of the tangent line. And in the last part, we need to figure out the arc lengths of this curve from 0 until pi. So the arc lengths of this curve can be found by integrating r prime and its norm with respect to the t from 0 until pi. So recently we figured out that the r prime is equal to this vector, and we can find its norm. So the r prime of t, its norm is going to be the square of the first component, which is going to be 4 sine square of tt. Square of the second component is going to be 4 cosine square of tt. And the square of the last component is going to be simply 9. So if I take out a 4 from these two terms, it's going to be 4 multiplied to the sine square plus cosine square, which is equal to the 1. And at the end, we'll get simply square root of 13. So the norm of the r prime of t, it's going to be square root of 13. And it appears we need to integrate the square root of 13 from 0 until pi with respect to the t, which is going to be antiderivative, square root of 13 t from 0 until pi. If I substitute the pi, it's going to be 13 from the square root multiplied to the pi. And if I substitute the 0, it's going to be simply 0. Let's discuss the second problem. In the second problem, we're given 3 points. So let's draw them on a flat plane. So let's assume that a P is here with the coordinates 0, 1, and -1. The second point Q is here was the coordinates 1, 2, and 3. And the third point O here is coming with the coordinates 0, 0, and 0. And actually we need to figure out the cross product, and then we need to figure out a plane which is lying on this, which is going through the 3 points. And at the end we need to figure out the area of this triangle. So let's create first of all the t vectors OP and OQ, the position vectors. Now we need to multiply these t vectors as a cross product. So let's multiply 1, 0, and -1 to the another vector 1, t is 3 as a cross product. And when we need to multiply the t vectors as a cross product, we need to find the determinant of the 3 by 3 matrix. So we can evaluate the determinant by going through the entries of the first row. We need to eliminate the first row and the first column and evaluate the determinant of this matrix and multiply this additionally to I. So I multiplied is the determinant of this matrix, which is obtained by multiplying this element, 3 multiplied to the 3, minus -1 multiplied to the t, it's going to be simply t, minus j multiplied to the determinant of the matrix, which is obtained by eliminating the column and the row where the j is located. It's going to be 1 multiplied to the 3, which is going to be 3, minus -1 multiplied to the 1 is going to be +1. And the k multiplied to the determinant of the matrix, which is obtained by eliminating the column and the row where the k is. And it's going to be simply t multiplied to the 1, minus 1 multiplied to the 0, which is simply t. So what we get is we'll get a vector which has the 3 components. So the coefficient before the I, it's going to be the first component of the vector, which is t. The coefficient before the j, which is -4, is going to be the second component of the vector. And the coefficient before the k is going to be the third component of the vector. So the cross product of these t vectors is going to be this vector. And actually this vector is going to be perpendicular to both of these vectors at the same time. So if you've got a plane, we can construct the plane through the t vectors. And if there is a vector which is going to be perpendicular to these t vectors, it's going to be perpendicular to all the vectors. It means that this is the normal vector of the plane. So the normal vector of the plane has the following components, t, -4, and t. And using the normal vector, we can construct the equation of the plane. So in order to do this, we need to multiply x, y, and z as a dot product to the normal vector. It's going to be t -4 and t. And this is going to be equal to the dot product of the normal vector as a dot product. So we need to multiply the normal vector as a dot product to one of the points on this plane. So you can choose any of the points. In all of the 3 cases, you're going to get the same answer. So for me, it's really comfortable to choose this point, 0 and 0 and 0. On the left-hand side, I will get tx minus 4y plus tz, and on the right, I will get simply 0. So please note that whenever you are given an equation of the plane, the coefficients before the x, y, and z, when they are all in one side of the equation, are going to tell you the components of the normal vector. And at the end, we need to figure out the area of the triangle as well. So we need to create a triangle through these 3 points. And actually, when you multiply these t vectors as a cross product, it's going to be a vector. And the norm of this vector is going to tell you the area of the parallelogram, which you can obtain using these t vectors. And the area of this triangle is actually the half of the area of the parallelogram. So once we found this vector, so the area of the parallelogram, or the area of the triangle, divided to the t, it's going to be, multiplied to the t, or the area of the parallelogram, it's going to be equal to the norm of the vector was the components t -4 and t. It's going to be the square root of 4 plus 16 plus 4, which is the square root of 24. And this is exactly twice area of the triangle. So this A which we found is the area of the whole parallelogram. And the area of this triangle is going to be square root of 24 divided to the t. So the area of the triangle is equal to the square root of 24 over t. So problem number 3 is about the tangent planes. So the equation of the tangent plane can be written as the partial derivative. So if the surface is given as a multivariable function, as in our case is e in the power of x and y, and then the equation of the tangent plane is going to be the partial derivative of the f with respect to the x at this point, with the components 1 and y multiplied as x minus x0, plus the partial derivative of the f with respect to the y at this point 1 and 1 multiplied to the x minus y0, y minus y0. And by the way, x0 is equal to the 1 and y0 is also equal to the 1. So when you're given a point, the first component is going to be x0, the second one is y0, and the third one is z0, is equal to the z minus z0, where the z0 is going to be equal to simply e. So the only thing which we need to find in this equation is the partial derivative of the f with respect to the x and y, and then we need to evaluate those partial derivatives at the point 1 and 1. So let's find the partial derivative of the f with respect to the x. It's going to be simply e in the power of xy multiplied to the derivative of the xy with respect to the x. So please note that when you are going to take the derivative from the function, multivariable function with respect to the x, so you need to look to the y as a constant. So that is why the derivative of the constant multiplied to the y, x, it's going to be simply y, the constant. And the derivative of the f with respect to the y, it's going to be e in the power of xy multiplied to the x. So when we evaluate this at the point 1 and 1, what we'll get is e in the power of 1 multiplied to the 1, or simply e. And when we evaluate this at the point 1 and 1, we're going to get again the e. So we just need to substitute everything to the equation, and we'll get e multiplied to the x minus 1 plus e multiplied to the y minus 1 is equal to the z minus e. So if you open up all the brackets, we'll get ex plus ey minus te is equal to the z minus e. So if we put everything to the right or to the left, or we can write down the z is equal to e multiplied to the x plus e multiplied to the y minus e simply. So let's go to the problem number 4. We're given a two planes in this form and in this form. We need to find the value of the q so that these two planes are becoming perpendicular. So actually, if the equation of the plane is given like this in a form of ax plus by plus cz is equal to some d, the components, so the coefficients before the x, y, and z, are going to tell me the components of the normal vector. So this is going to be a, b, and c. So the normal vector of the first plane is going to be q, 1, and 1. In the normal vector of the second plane, it's going to be the coefficient before the x, which is 1, the coefficient before the y, which is minus 1, and the coefficient before the z, which is 5. So you need to be careful when you choose the components of the normal vector. So all the three variables, x, y, and z, should be in one of the sides of the equation, either in the right-hand side, either in the left-hand side. So now, we need to find a coefficient. So we need to find a condition so that these two vectors becomes perpendicular. So if the two normal vectors of the planes are perpendicular, it means that the planes are perpendicular as well. Two vectors are perpendicular if the dot product is equal to the 0. So let's multiply these two vectors as a dot product. It's going to be q1, 1, multiplied as a dot product is a vector 1, minus 1, and 5. So this is going to be q minus 1 plus 5, and this should be equal to the 0. So from here we can obtain that a q should be equal to the minus 4 simply. So for this value of the q, so these two planes are going to be perpendicular. Problem number 5 is about the directional derivatives. So we are given a function f, and we need to figure out the directional derivative of this function at this point in the direction of this vector. So please note that the directional derivative of some multivariable function is obtained by multiplying the gradient vector of this function at this point x0 and y0 multiplied as a dot product to the unit vector in the direction of this v. So first of all, we need to evaluate the gradient vector. So the gradient vector of the f is going to be a vector which has two components. The first component is going to be the partial derivative of the f with respect to the x. The second is partial derivative of the f with respect to the y. If you have the function in the form x squared minus 5xy, its derivative with respect to the x is going to be simply tx minus 5y, and its derivative with respect to the y, it's going to be simply, so this is going to be 0, and the derivative from this part is going to be minus 5x. So the gradient vector of this multivariable functions is going to be tx minus 5y, and the second component is going to be minus 5x. So we need to evaluate the gradient vector of this function at the point 1 and 2. So basically, I'm going to substitute for all the values of the x, 1, and all the values of the y will be 2. T multiplied as a 1 minus 5 multiplied as a t, it's going to be the first component of this vector, minus 5 multiplied as a 1 is going to be the second component. So let's try to simplify this. So t minus 10 is going to be minus 8, and the second component is going to be minus 5. So this is the gradient vector at this point, and now we need to figure out, so let's say v vector is given some vector like this. The ending points are going to be 3 and 4. So please note that if the vector is given as in this form, 3i plus 4j, you can write down this v vector as a 3 and 4 using in the form of two tuple. So we need to figure out a vector, unit vector here, which is going to be in the same direction as this vector. So please note that you can obtain the unit vector in the direction of the v by dividing the v to the norm of the v. So the v vector is 3 and 4, and we have to divide this to the norm of this vector, which is 9, 3 in the square, plus 4 in the square, which is 16, which is going to be square root of 25, which is simply 1 over 5, which is simply 5. So this is going to be 1 over 5 multiplied to the 3 and 4. So the directional derivative of this function in the direction of the u, it's going to be minus 8 minus 5 multiplied as a dot product is a 1 over 5, 3 and 4. So we can multiply these two vectors as a dot product and multiply this at the end to the 1 over 5. So let's multiply these two vectors as a dot product. It's going to be minus 8 multiplied to the 3, minus 5 multiplied to the 4. So this is going to be 1 over 5 minus 24 minus 20. It's going to be minus 44 divided to the 5. So this is the value of the directional derivative. So actually geometrically it means, or physically it means, how much the surface, how fast the surface is changing in this direction of the vector v. So the second problem asks us what is the maximum rate of change of the surface at this point? In which direction and what is this? The direction at which the surface is changing at maximum would be the direction of the gradient vector at this point, which is going to be minus 8 and minus 5. And the absolute value of the maximum rate of change would be the norm of this gradient vector, which is going to be 8 in the square, 64, plus 5 in the square, which is 25. If we add them, it's going to be 89 from the square root. Problem number 6 is about the line integrals for the scalar functions. This is our scalar function, f of x and y. This is given like this, and we need to evaluate the line integral through the line segment from this point until this point. So the equation, the vector equation of the line segment is given. So the initial point was the coordinates 4 and 5 multiplied to the 1 minus t, plus the ending point was the coordinates 1 and 1 multiplied to simply to the t. So let's multiply 1 minus t to each of the components of these vectors and t to each of the components of these vectors and add them. So this is going to be 4 minus 4t, 5 minus 5t, plus, so when you multiply 1 and 1 to the t and to the t, it's going to be t and t. So now if you add these t vectors, you need to add them components-wise. So the first component to the first, second component to the second. So the first component is going to be 4 minus 4t plus t is going to be 4 minus 3t. And the second plus second is going to be 5 minus 5t plus t, which is going to be 4t. So now we can evaluate the line integration. So please note that whenever we're given the vector function, the first component tells me the x component of the points on this line, and the second one tells me the y components. So basically x of t is equal to the 4 minus 3t, and y of t is given as the 5 minus 4t. And at the same time, we can write down the line integration of this function, 2x squared minus y, along this line with respect to the arc lengths, is the integration of this function when it depends on a t only. So in order to do this, we need to substitute the x with this function and the y with this function. So this is going to be the integration of the t multiplied to the 4 minus 3t in the square minus 5 minus 4t. And this is multiplied to the norm of the r prime of t, and we have to integrate this then with respect to the t, where the t is going to change from 0 to the 1 for the line segments. So the only thing which we need to do is we need to simplify this term, then also we need to find the norm of the r prime of t. So if the r of t is given as the vector 4 minus 3t and 5 minus 4t, then the r prime of t is equal to the minus 3 and minus 4. Right? So the derivative of this function, which is minus 3, derivative of this function, which is minus 4. And its magnitude, the magnitude of the r prime of t, it's going to be the square root of the first component, which is 9, plus the square root of the second component, which is 16, and we need to add them and take the square root, which is going to be square root of 25, which is 5. So now let's try to simplify this expression. It's going to be the integration from 0 to the 1 multiplied to the square root of 25, or simply 5, which is the r prime of t and its norm. Now let's open up the brackets. It's going to be t multiplied to the square of this term, which is going to be 16 minus 24t plus 9t squared minus 5 plus 4t. So let's try to multiply this t to all the terms in this brackets and simplify them. It's going to be 5 multiplied as the integration from 0 to the 1. 30t minus 48t plus 18t squared minus 5 plus 4t dt. So we can simplify this still. So 30t minus 5, it's going to be 27. Minus 48t plus 4t, it's going to be minus 44t plus 18t squared. Let's find the antiderivative of this function. It's going to be 5 multiplied to the 27t minus 20t t squared plus 6t cubed. This is the antiderivative, and we need to validate this at the 0 and 1. So obviously if you substitute the 0 to all the t's, it's going to be 0. And when we substitute the t was to be equal to the 1, it's going to be 5 multiplied to the 27 minus 20t plus 6. It's going to be, so 27 minus 20t is 5, plus 6 is going to be 11, which is 5 multiplied to the 11, or 55. So if we would like to express the function in terms of the Taylor series, we need to write this as f of x is equal to the infinite sum. N goes from 0 to infinity. So this is f n's derivative of this function at some point a divided to the n's factorial multiplied to the x minus a in the power of n. So the Maclaurin series, it means that we need to express this function when the a is equal to the 0. So basically f of x is going to be equal to the summation of n goes from 0 to infinity f of n at the point 0 divided to the n factorials. So please note that this means the n's derivative of the function multiplied to the x in the power of n. So let's write a couple of first terms. So this is going to be f of 0 when n is equal to the 0 plus f prime of 0 divided to the 1 factorials multiplied to the x plus ft primes of 0 multiplied to the x squared divided to the t factorials plus f3 primes at the 0 multiplied to the x cubed divided to the 3 factorials, and so on. So we need to figure out a coefficient before the x cubed, right? Or basically this coefficient. So in order to do this, we need to find the 3 derivatives of this function. F of x is given as the sine of x. So the first derivative of this function is going to be cosine of x. So the second derivative would be minus sine of x. And the third derivative would be, again, a cosine, but with a minus. So we need to evaluate this third derivative at the point 0. It's going to be minus cosine of 0, which is minus 1. And the coefficient before the x cubed would be the third derivative of this function at the point 0 divided to the 3 factorials. So this is going to be minus 1 divided to the 6, or minus 1 over 6 simply. Let's discuss the problem number 8. So in the problem number 8, we are given a vector field in the form of f of x and y. So we can write this as a t-tuple in the form of y and 1 minus x. So we need to integrate the line integration over this curve C, which is the portion of the ellipse, which is given in this form, in the fourth quadrant, which is moving in the counterclockwise direction. So if you remember, so if you're given the equation of the ellipse as in the form x squared divided to the a squared plus y squared divided to the b squared is equal to the 1, we could write down the parametric equation of the ellipse in the form x of t would be a multiplied to the cosine of t, and y of t could be written as the b multiplied to the sine of t. So what we need to do is we need to define this curve first of all. So the ellipse is a vector function, can be written as, in our case, the a is equal to the 2 and b is equal to the 3, right? So here it should be a squared, which is 4, and b squared, which is 9. So that is why the vector function of the ellipse, it's going to be 3 multiplied, So the vector function of the ellipse can be written as a t multiplied to the cosine of t and 3 multiplied to the sine of t. This is going to be an ellipse which is on the fourth quadrant, counterclockwise direction. It means that we are moving in this direction. And this angle is minus pi over t. And this angle here is going to be 0. So the t is going to change from minus pi over t until 0. So we can write down the line integration in the vector fields as a dot product of the f to the r prime of t. And we need to integrate this with respect to the t from minus pi over t until 0. So when we substitute the f with this function, we need to be careful with this because we have to substitute the y and x with this equations. So this is going to be the integration from minus pi over t until 0. So f of 0, f, the vector field, is given as a vector. The first component is y, which is 3 multiplied to the sine of t. And the second component is 1 minus x, which is going to be 1 minus t cosine of t. And we have to multiply this as a dot product as the r prime of t. So if the r of t is given like this, the r prime of t is equal to the minus t sine of t and 3 cosine of t. So we have to multiply this to the minus t sine of t and 3 cosine of t. And we have to integrate this with respect to the t in this range. So let's first of all multiply this t vectors as a dot product. So it's going to be the first one to this. It's going to be minus 6 sine square of t. So this vector, so the second component multiplied to the second component of this vector, and we have to sum them. So it's going to be 3 cosine of t multiplied to the 1, which is 3 cosine of t simply. And this is going to be minus 6 cosine square of t. And we'll have to integrate this with respect to the t. So actually, if I take out this minus 6 and minus 6 from the first and the third terms, what is left inside the brackets are going to be sine square of t plus cosine square of t, which is equal to the 1. So that is why we can write down this integration from minus pi over t until 0 of the 3 cosine of t minus 6, and we need to integrate this with respect to the t. So the antiderivative of the first term is going to be 3 sine of t, and the antiderivative of the second term is going to be minus 6t. So we need to substitute minus pi over t and 0. So let's substitute the 0. It's going to be minus 3 multiplied to the sine of 0, minus 6 multiplied to the 0, simply 0. And minus, we need to substitute minus pi over t. It's going to be 3 multiplied to the sine of minus pi over t, and minus 6 multiplied to the minus pi over t. And actually, this term is 0, this term is 0. Sine of minus pi over t is going to be minus 1. So with this minus, it's going to be plus 1, which is simply 3 here. And minus, was this minus, it's going to be plus, but was this minus, it's going to be again minus 3 pi. So this is the value of the line integration in a vector field. And the last problem is about the double integration over the general region. So we need to evaluate the double integration of this function in the region of D, which is defined as a region between these two curves. So in the first part, let's define this region. So I would assume that you know how the x is equal to the y square looks like. So this is going to be parabola on the x-axis, where all the points are going to have the positive x points, right? And when we have a curve x is equal to the minus y square, it's going to be this parabola, which is reflected over the y-axis. So all the components of the points, all the x components of the points along this parabola are going to be negative. And the second curve is x is equal to the y minus x, or we can write this as y is equal to the x plus 6. So this is going to be a line. In order to draw this, we need to find the t points. So in order to do this, let's substitute the x to be equal to the 0. In this case, y is equal to the 6. So this is going to be, the first point is going to be here, 6. So if you substitute x to be equal to the minus 6, y is going to be 0. It's going to be some point here. So this point has the coordinates 0 and 6. And this point has going to cause the coordinates minus 6 and 0. So if we connect them, this is going to be this line. And our region is defined here. So we can define this region by changing the x, by changing the y from here and here. And the x coordinates of the points would be changing from this line until this curve. So in order to do this, first of all, we need to find the intersection points here and here. So we can find the intersection points by solving the system. X is equal to the minus y squared, and x is equal to y minus 6. So if you equalize them, you will get minus y squared is equal to the y minus 6. If you put everything to the right or to the left, it's going to be y squared plus y minus 6 is equal to the 0. So you can write down this as a y minus 3, or plus 3, sorry, multiplied as a y minus 2. So it means that the roots of this equation are y1 is equal to the minus 3 and y2 is equal to the 2. So now we need to evaluate the function, evaluate the x coordinates of the points. So by substituting the y1 to one of this equation, we can obtain the x coordinate, x1. It's going to be minus 9. And if you substitute this y2 to the one of the equations, you will get xt, which is going to be minus 4. So this point here was the coordinates minus 4 and 2. And this point here has the coordinates minus 9 and minus 3. So we can define the region, our region, as a set of points x and y, where the y would change between minus 3 and 2, and the x changes between these two curves. So the x changes between this line, which is lefter, right? So this is going to be the equation. So this equation should depend on y. So this is going to be y minus 6 until this one, which is more righter, which is going to be minus y squared. So we need to still evaluate this integration, 6xy over this region. So let's integrate it. So we need to integrate 6xy with respect to the x first of all, because x changes between the two functions from y minus 6 until minus y squared. Then we have to integrate this with respect to the y, where the y would change between minus 3 and 2. So let's first of all integrate it in an integration. So this is going to be the integration of the 6yx with respect to the x, where the borders are these two functions. So the antiderivative of this function is going to be 3yx squared, and we need to substitute minus y squared and y minus 6 to here. So if you substitute the x with the minus y squared, it's going to be 3y multiplied to the y in the power of 4 minus 3y multiplied to the y minus 6. So if you open up the brackets and simplify this expression, it's going to be 3y in the power of 5 minus 3y squared plus 18y. So now this is going to be our inner integration. We need to integrate this with respect to the y. 3y in the power of 5 minus 3y squared plus 18y should be integrated with respect to the y from minus 3 until 2. So this integration is going to be, first of all, we need to take the antiderivative. It is going to be 3y in the power of 6 divided to the 6 minus 3y cubed over 3 plus 18y squared over 2. So if we evaluate this function by substituting t and minus 3 in terms of the y, we will get 412.5 with the minus.